So there's three momentum equations you'll see on the reference table here. P equals mv, P before equals P after, and J equals F net T times delta P. So your net force times your time is your change in momentum. And these come out of Newton's second and third laws, really. And as a reminder, the third law says that every force has an equal and opposite force on a different object. I don't know if I told you that. Meaning, if you push with 30 newtons on one object, you got to have 30 newtons on the other object. They might not have the same acceleration because acceleration is net force over mass. So if they have different masses, they will have different accelerations. But you can combine this third law, second law, and you come up with these impulse momentum kinds of problems. They are both vectors. You know, as I said, this points in the same direction as velocity, and this points in the same direction as your net force. And so this would be in kilograms meters per second, and this would be also kilograms meters per second, or newtons times seconds, force times time. And there's a couple different kinds of problems that you're going to see when it comes to momentum and impulse. A common one might involve two different objects with forces acting on them. So let's say, for example, we have 10 kilogram and a 2 kilogram object, and they have two forces, F1 and F2. And whatever that force is, maybe it's 100 newtons. And so you got two objects, same force. Your acceleration should be net force over mass. So you end up getting, for object 1, 100 newtons over 10 kilograms. So that has an acceleration of 10 meters per second squared. And this one has an acceleration of 100 newtons over 2 kilograms. So 50 meters per second squared. So these accelerations end up being dramatically different, which means that if you go for a certain amount of time, which is where the force times time thing comes in, their speeds will be different. So their final velocity after they separate, for whatever time that is, will differ. And that's where momentum impulse stuff comes in. So sometimes you might see it expressed as basically like one object problems where it's involving force and time and some sort of change in velocity. Maybe you know the mass. Those are the variables. Sometimes you might just be asked like, hey, what's the impulse or what's the momentum? But let's try to come up with something a little more meaningful in this. So we can say, for example, there you go. You kick a ball. It's a 2 kilogram ball, and velocity goes from 0 to 5 meters per second. Let's make it smaller. In the impact time, meaning the time over which the ball acts, is 0.1 second. Pretty small. So impulse is delta P, that's equal to force times time. Turns out we don't even need the J in there, we can just use this part of it. So let's see, delta P is going to be mass times the change in velocity, or mass times V final minus V initial. So mass is 2 kilograms, V final is 5 meters per second, V initial is 0 meters per second, and that's going to equal a force times a time of 0.1 seconds. So we get 2 times 5 equals force times 0.1. So that's 10, and your force ends up being 100 newtons. And just combine and solve for the thing that you don't know. Let's say instead you kick a ball, and it's just like before, 2 kilograms, but velocity is going to go from, we'll say negative 5 meters a second to 5 meters a second. And it's common for people to be like, oh, it's the same speed. It's got no impulse. And that's not true because the velocity's directions changed. To go from -5 to 5, it's switched directions. It's had a total change in velocity of 10 meters per second. So now 2 kilograms times V final is still 5 meters a second, minus your V initial, minus a -5 meters per second, equals force times, and again, we'll just stick with 0.1 seconds. So now we get 2 times 10 meters per second is your change of velocity, equals force times time of 0.1 seconds. And so you solve for force, you get 20 divided by 0.1. So now you got twice as much force. So make sure you identify the directions correctly when it comes to these sorts of problems. The other kind of question that you often see with impulse and momentum is conservation of momentum. And that's basically saying P total is constant, your total momentum is constant, or as they like to write here, P before equals P after. And that's typically involving two objects. Then these objects could either collide or they will often separate too. Separate could be like an explosion, or they could spring apart, or they could push off of each other, like two ice skaters pushing off in opposite directions, etc., etc. So let's say that we have two objects moving towards each other. I'm going to say this is 10 kilograms, this is 5 kilograms. Let's say this velocity is 2 meters per second. This velocity we'll say is -3 meters per second. You typically need to know a little bit about what happens afterwards too, but let's just find out P before, which is 10 kilograms times 2 meters per second plus 5 kilograms times -3 meters per second. And that's just mv, right? m1 v1 plus m2 v2, initial momentum. So 20 minus 15 equals 20 minus 15 equals 5 kilogram meters per second. That's my total momentum. So P after the collision is still going to be 5 kilogram meters per second. Now you might know one of them. Maybe you know that one of the objects comes to a stop. Or maybe you know that the velocity of one of them is given. Maybe you know they stick together. So if they stick together, that means afterwards you've got an object that has got a total mass of 12 kilograms that's going probably to the right because its momentum is going to be positive. So you could say, hey, mv is going to still be 5 kilogram meters per second, where mass is now the total mass, 12 kilograms times v equals 5. So velocity is going to be 5 over 12. Which is 0.42 meters per second. Because let's give our answers in decimals. So there's lots of different ways to do these sorts of questions. Be aware, just when you know this, if you figure out the initial momentum, it's going to be equal to the final momentum. You're often going to see, as I said, explosions as well, or separation. And so imagine this. Two pieces fly off in opposite directions. Well, before they fly off, the velocity for both of them was 0. So P before is going to equal this mass, whatever this is. Let's keep it, let's say 10 kilograms and 5 kilograms is just 10 times 0 plus 5 times 0, which is just 0 kilogram meters per second. So P after has got to be also 0 kilogram meters per second. What does this mean? That means if they fly off with a V1 and a V2, P after, which is 0, is going to be 10 kilograms times V1 plus 5 kilograms times V2. So these two have to add up to each other, or you could just say, hey, 10 kilograms times V1 equals negative 5 kilograms times V2. And probably you would have a velocity. So let's say if V2 is equal to 7 meters per second, then V1 is going to be equal to negative 5 kilograms times V2, which is 7 meters per second, over 10 kilograms, which is going to be negative 3.5 meters per second. And you will notice that the less massive object has a higher velocity, the more massive object has a lower velocity, probably because the less massive object had a bigger acceleration, and the more massive object had a smaller acceleration for the same amount of time. So with these kinds of questions, just figure out whether you know what you know and plug them in, keeping in mind that you could, in theory, solve these also with Newton's laws if you really wanted to, combined with kinematics and things like that. I think that about does it for this quick review. So thank you very much for watching, and good luck with everything. Please, please, please don't hesitate to let me know if you've got questions. Bye.